Welcome to the galvanic cells summary little video. So galvanic cells, also known as voltaic cells, they are basically represented by two half cells that react, and it's a redox reaction where electrons are being transferred by two different electrodes, but we'll get to that just now. So all galvanic cells are spontaneous. Chemical energy is converted to electrical energy. So the chemical energy is stored within the electrodes. We'll get to that just now, the substances that we are putting in solution. Electrons are being transferred, and it's also an exothermic reaction. So heat is being released into the environment, right? And electrons are being transferred between, let's just say, I made a little example here, but like copper and iron. Electrons are being transferred from the one to the other. We'll be able to decide later. But because electrons are being transferred, it's going to result in a redox reaction. Now, we should know this very well from grade 11. Something's being oxidized and something's being reduced. But in this case, electrons are being transferred from that which is being oxidized. In other words, electrons are being released. Remember, oil rig, eh? Electrons are being released and they go to the thing that is reduced where electrons are being accepted. All right. So remember, something that's oxidized is a reducing agent, and something that's reduced is an oxidizing agent. So if something is being reduced, it will oxidize the other thing. That's what it means from grade 11 work. So we have a basic setup here, so I can just explain what's going on. I've labeled number 1 and 2. This is an electrode. Let's just take that out there. We have these two bars or electrodes that are in a solution. So what happens is it'll be two metal bars. We'll come to an exception later with gases, but like let's just say we have an iron electrode and we have a copper electrode. That's what it will be, and we connect it up to a voltmeter up here, and electrons will be sent either from iron to copper or copper to iron, depending on our work we can do just now. So the iron, looking at the iron electrode over here, it will have a solution, as you can see, and it will be the ions of that electrode. It's bonded to some type of like iron sulfate or iron something that can dissolve in water. So usually let's just take a sulfate here. Let's hope that dissolves in water. If not, yeah. So don't like the video then. But iron sulfate, for instance, let me just check if it can dissolve. All right, so iron sulfate is soluble in water, so you have to like the video, like and subscribe, for quality videos, more quality videos like this, just whatever. Anyway, let's just carry on. Now, so for copper, if you look at the second electrode on the right here, we have copper. What must be in the solution then? The copper ions, right? Which is combined, it's going to be some type of compound that, let's just make it copper sulfate as well. That'll also be soluble in water. So copper sulfate, but it has to be this electrodes. Ions must be in solution. All right, and then we have this gray thing, which is a salt bridge. So what happens is, let's just say iron is going from iron as a oxidative state of 0 to an iron +2 state in this reaction. So it is releasing electrons in? Yes, because Fe0 goes to Fe2+. We know this from grade 11. So to balance this little half reaction, we have to add 2 electrons here. So we're starting and we are producing 2 electrons by the iron. So what's happening is then electrons are being released by the iron electrode over here. So the electrons are going to move like this, like this, like this, and we'll get here, and then the charge will be carried by the ions. And if there's no salt bridge, there's no completion of the circuit. So that's why that salt bridge is there, so that the circuit can be completed. And in the salt bridge, usually a nice thing to put in here would be like a potassium nitrate solution, because any compound with potassium will be soluble in water, and any compound of nitrates will also be soluble in a solution. So there won't be nothing will precipitate out and form a solid in that tube, which will be a disaster. So we have a complete circuit, and the charge will be able to move, and boom, we get a reading on our voltmeter, and everything's hunky-dory. So first thing I want to talk about, or not the first thing, but one of the things is we have the current direction. Now, current direction, remember in grade 8, 9, 10, 11, 12, we learn about the conventional current direction. We're not going to talk like that. We're going to talk about the electron current direction. Okay, now for galvanic cells, it will be from the electrode, that's the bar of iron or a bar of metal. It will go from what is oxidized, oxidized to that, the electron direction will be from the thing that's oxidized, in other words, producing electrons, to the thing, the electrode that is being reduced, which is accepting electrons. That's your current direction. We're talking about electron direction. All right, it's very important to think in terms of the electrons going through the wire at the top here is a nice way to indicate. So let's just say iron is producing ions, so it's ions is going into solution. The electrons will form up, go like this, in this direction, so in that direction there. Okay, but if copper was producing ions, then obviously then the electrons will go in the other direction. Okay, quite important to know that. All right, and so the anode and cathode, what is an anode and what is a cathode? So an anode, the anode is where, it's the electrode where oxidation takes place. And this is true for the next section as well, so it's like a nice hard rule. So a little thing you can think about is it's oxan. Oxidation at the anode, remember oxidation is the production of, or a loss of electrons or producing of electrons from that substance in a redox reaction. So if we take a look here, and we said that iron produces, let's just say it is like this, we can take a look later if we are correct, but let's just say iron goes to a state from a 0 state to, and it gets oxidized to Fe2 plus, electrons are being released there by the iron electrode. So if it's being oxidized there, is this not then the anode? Oxidation, so anode. Easy peasy, eh? And the opposite then is true for cathode. So cathode is where reduction takes place, and this is true for the next section as your electrolytic cells. So it's a really nice thing to memorize so you don't get confused. Very important to memorize this. And the little acronym people use is REDCAT. So reduction at cathode and oxidation at the anode. REDCAT. You know, you think of little. Yeah, here we got some red cats. You know, red. Look at that, eh? Nice red cats. So yeah, all that ginger cats. I don't know what you call them. No offense. All right, so okay, we've got the red cats. So we can always remember that reduction is at the cathode and obviously then oxidation at the anode. But very important to understand that to memorize it. All right. Now, if we take a look again at this iron electrode and it's forming iron is forming ions, almost all. Okay, so the iron electrode is producing iron ions. Okay, what is the mass? What's going to happen to the mass of this electrode? So the solid iron, which has an oxidation state of 0, will be going into solution. So you can actually be using up the particles or the atoms in that electrode to form ions in solution. Okay, and that will result in a loss of mass in your iron electrode. Now, if you take a look at copper is being, in this hypothetical case, is now accepting electrons. And so it is going from the ions in solution are going to form on that copper electrode. So copper 2 plus is going to accept electrons from the iron electrode. And it's going to form copper as a solid, right? With an oxidative state of 0. And that's going to pile up on that electrode, increasing the mass of the copper electrode, which in this case is the anode or the cathode. Remember, REDCAT, reduction. Is this not being reduced? Reduction of the oxidative state, reduction. So REDCAT, cathode, reduction cathode. So copper here in this case will be a cathode, if indeed this is just the hypothetical case. All right. Yeah, I said it's a hypothetical case, but by chance, it actually happens like this as well. All right, so that's pretty simple so far. Now we said oxidation takes place at the anode. Now, just for galvanic cells, not for electrolytic, if we have this iron forming Fe2 Fe2 plus 2 electrons, will the anode, where oxidation takes place, will it be positively charged, or will it be positive or negatively charged? It will be negatively charged. Negative, because electrons are released over here, okay? So therefore, by the cathode, it will be positively charged because the electrons are being accepted. All right, so let's take a look at the half reactions and a net cell reaction. So we can write the reduction half cell reaction, and we can take a look at the oxidation half cell reaction, and you get a net at the end there. All right, so the reduction half cell reaction, remember, red cat is where the cathode is, or where reduction takes place. We did decide earlier that the Cu2 plus goes to Cu0. So that is where reduction takes place, and this is where oxidation takes place by the electrodes, and all the half cell itself. And then, so we can take a look at what's the first one we want to do again? Reduction. So let's do the reduction first. Copper. What's happening in this half cell over here? Copper 2 plus is going to copper 0. So let's write that down. Always leave a nice little gap. There's a tractor outside. Oh well. And then oxidation. At the oxidation half cell, we have iron from 0 going to iron 2 plus. Leave a little gap here in case when you put electrons somewhere or multiply something. Fe2 plus. So what is happening to balance this out? There's many ways you can think about it, but the electrons will have to be accepted here by the copper, 2 of them, and here they're being released as 2 of them. And just remind ourselves, here is the increase in mass of the copper electrode, or the red cat, the cathode, and there's a reduction in mass of the oxand, the anode. Oxidation takes place at the anode. Now, from grade 11, you should remember, we have to now focus on the number of electrons and sort of LCM the thing to multiply these two chemical equations so that they balance out perfectly. But luckily for us in this case, we just have 2 electrons. So we can just add these two together. So we have Cu2 plus Fe, and that will go to Cu plus Fe2 plus. So we just have to put the subscripts in. That will be aqueous, it's in solution. Iron will solidify. It starts as a solid. Copper 2 plus is in solution, and it will go to a copper 0, right, which is a solid. And the iron in the electrode will go into solution, which will be aqueous. All right, and there's your net cell equation. Let's just write the cell equation. Oops. Not too difficult, eh? I'll do like one different thing, just so we can see. But like, we just take a nice little look quickly. It's actually grade 11 work, but what's happening to copper 2 plus? It is being reduced or oxidized. Remember, we have a 0 charge. So there is a reduction in the oxidative state there, so it's being reduced. So copper 2 plus, Cu2 plus, is being reduced. Therefore, it is an oxidizing agent. You guys remember from grade 11, it's very important to maybe go over that again by yourself, right? It's very important. And same for iron, not the same, but iron will is being oxidized from Fe0 to Fe2 plus, being oxidized. Therefore, it is Fe is a reducing agent, meaning it's causing the other thing to be reduced. All right, some new work. We have cell notation. Cell notation is quite simple if you just have a little pattern to follow. So what happens is this. We have anode, streepie, vertical line, to anode, electrolyte, that's a solution. Salt bridge, that's double, it's like, that salt bridge is the double line. And then we have cathode, electrolyte, that's the solution. Well, it's all cathode electrolyte to the cathode. Okay, so with our example we just did now, where we have iron being oxidized and copper being reduced. So what is the anode? Remember, oxan. So what's being oxidized? Iron. So iron is by the anode. So you write down what's the anode is the iron is the electrode. So it'd be iron going to anode electrolyte, iron 2 plus, salt bridge, and cathode electrolyte. Not cathode, it's like a mirror. Cathode electrolyte, you see the mirror, it's like, this is like a mirror, so it's like points out that way. All right, so we have cathode electrolyte. What is our cathode? Cathode is red cat, like we saw earlier, a red cat, which is what is being reduced. That's being reduced. So, but it's in its Cu2 plus is being reduced, which is the electrolyte, so Cu2 plus, and it goes to the cathode, which is the red cat, the CuO, the solid. Okay, so we just have to put the subscripts in as S, AQ, and S. Easy peasy? Yes? No, it's quite nice, eh? So just again, we have anode electrolyte, cathode electrolyte, and we just have salt bridge symbol over there, right? So it's not that bad. But if you know red cat and you know oxan, you are fine with this pattern that you will memorize, okay? So no matter what two electrolytes or half cells we have, we can always just go in this pattern and rewrite it as is, and it's quite simple. Now, if, let's just say, the anode or cathode is not a solid, or it's not a metal or whatever, we will use a platinum metal in most cases. So let's just say the anode was hydrogen. I'm just making something up here. It's hydrogen gas, and it goes to an H plus there. Just ignoring the right hand side now. So it's a gas, so you have to actually put in the electrode you're going to use that will allow this reaction to take place, and usually it's PT, so we can write PT, or sometimes it's carbon, depending on the situation. So you just write this extra piece there, that little extra platinum on the left of the anode, or if it's on the right, you write it on the right of the cathode. It's like a mirror, remember? Everything moves from salt bridge out. Electrolyte to the electrode to the, if there is a inert electrode that will work with a gas. All right. So for example, let's just say we have a situation where we have two gases reacting with each other. So you get fluorine going to a fluoride ion. So there will be a reduction there. Remember, a reduction. So this will be reduction. And over here we have oxidation, because it's an increase from a -1 to a 0. It's an increase in the oxidative state. So how do we write this down as in this notation? So let's take a look. So we write anode first. Now anode, remember, is oxan. What's being oxidized? That, right? So we write it down. What is the anode? It will be Cl2. What is the solution? Cl minus, because it's the ion. And then, remember, we don't put the balancing numbers in there, but it's a gas. So it's a gas by the anode. So we need an inert electrolyte that we can use. So we're going to use, in this case, platinum. And for the cathode electrolyte, remember, cathode is red cat, reduction, cathode. So we have in solution by the electrolyte, so not iron. And at the cathode, we have a gas being bubbled in, and then we have the actual electrode being used over there, all right, for gases. So if there's no gas, we don't care about that. All right, awesome. Now, if you take a look at the salt bridge is used to compute the circuit, the ions. Remember now, if you're producing ions, let's just take a look up here. Iron is throwing ions in solution, or such a bad idea to pick iron. You'll actually increase the concentration of Fe2 plus ions, and they will have to sort of start going into this salt bridge to keep the whole system neutral. Otherwise, if you are producing an excess of these, like start a positive charge, and that's not a good idea. It's going to weaken your system, cause the voltage to drop. So they'll have to go through there, right? They'll start like moving in there, so that we keep that half cell electrically neutral. And then, so as I say, the ions move towards the other half cell through the salt bridge to ensure neutrality in that half cell. Its use is to separate the two electrolytes, so that they do not mix the two solutions or the two half cells. And yeah, the electrolyte, the ions in solution that they do not react with the other ions in the other half cell. So we use usually a nice one, a compound to use in that salt bridge is potassium nitrate, because if something combines with potassium and forms another compound, it won't precipitate out. And same with the nitrate. Any compound with a nitrate will always dissolve in water, and any compound that's combined to potassium, let's just say potassium sulfate, right? That will dissolve in water. It's aqueous, it will dissolve. It won't precipitate out. It won't form a solid. So they don't form precipitates. All right. So that's the use of the salt bridge. Very important question. I love asking about a salt bridge. So just take a nice look at that. All right. So let's take a look at the movement of charges. Let's just go through the diagram. I did explain this earlier quickly, but your starting point, let's just make this or this the starting point. So where are the electrons being produced? Is where it's being oxidized, right? So iron is being oxidized to Fe2+. So it'll produce electrons that will carry charge in this direction to there, and we'll give it these electrons over to copper, so that the copper 2 plus ions will form a copper solid on that copper electrode, increasing its mass, right? And then through here, ions carry the charge to iron, and then so the whole pattern or direction or circuit is completed in that direction. So electrons travel like this, carrying charge, and then ions carry charge through the salt bridge. All right, quite simple. So again, where it's being oxidized, or where the reducing agent is where the electrons will form. So it will always go from the electrode being oxidized to the electrode being reduced. Okay, so let's take a look at the standard hydrogen electrode. It is just this little piece here, the electrode, the one half cell. So when using a voltmeter to measure the difference in potential, what am I saying? The potential difference between these two half cells, we use this hydrogen electrode and we give it a value of 0 volts, right? So we can always identify the E0 value of the other half cell, whatever the electrode is made of. So if you take a closer look at the hydrogen half cell, what happens is you pump in hydrogen in this glass tube and it gets bubbled out through here, forming an acidic solution at exactly 1 mole per cubic decimeter concentration at a specific temperature of 25 degrees, and there'll be H ions in the solution. And remember when I spoke earlier about, remember when I spoke earlier about if you use a gas, you can use like this electrode over here, and that will be a platinum electrode. That will be connected to a wire and connected to the cell, and then you have a complete circuit. We'll decide on the direction now. And on the right, we're going to put a zinc and then a copper, and you see what happens, right? So we have a H2 electrode and then a zinc electrode. So so I hope that makes sense. We have our salt bridge here. So let's just say we have a KNO3 solution in there. So what happens? What happens at the hydrogen half cell? Is it going from H2 to H plus? Or is it going from H plus to H2? Is it being oxidized or reduced? And what's happening to the zinc? Is the zinc electrode losing electrons, producing electrons? Or is the zinc electrode producing electrons, or the zinc ions in solution being reduced? So is there oxidation taking place, or is there reduction taking place there? So we use this table of standard reduction potentials at 25 degrees to decide which substance is being reduced or oxidized. So let's take a look. All right, so there's a pattern to this. It's pretty simple. The thing above, starting by, let's just say, whatever this is, if it's above the other one, it will go in that direction, and if there's something below it, it will go in that direction, starting on the left. So remember, we have in this case, we have a zinc electrode. Let me just go to the picture. We have a zinc electrode, and it has zinc ions in its solution. Then we have H2 as a gas, and it forms or it has H plus ions, an acid in solution, an acid solution. So which way is this going? Is the H plus going to form gas, or is the gas forming the H plus ions? And the same question is the Zn2 plus forming zinc metal, or is the zinc metal forming Zn2 plus ions? So we use this system over here. So let's take a look. Where's our zinc going to Zn2 plus, zinc 2 plus? There it is. And where's our H2? Our H2 is over here. So what we have, these two substances. Now, the thing above will always go left, and the thing at the bottom will always go right. So that is how that works. All right, so as we saw here, the zinc will form zinc ions. Is that a reduction or oxidation? It's an oxidation. Going to left's oxidation, and going to the right is your reduction direction. All right, so we said that Zn will go to Zn2 plus. So this one is being oxidized, so it's the reducing agent. And we said also that H plus will go to H2, and that is your reduction. So it's a plus 1 and it goes to a 0, right? So there's that. Now, so let's write down the two half reactions. So it's oxidation half reaction and our reduction half reaction, and then our net cell reaction. And we could look at our notation. Right. So if we take a look at this, what's being oxidized? We said that Zn is being oxidized, so Zn goes to leave a little gap there. And then reduced is our hydrogen. All right, so with these redox reactions, we have to get the electrons the same. So we're going to multiply everything here by 2, every term. Oops, sorry. I read that wrong off our table. Careful of that. So if you read it off that table, you'll get that. Right, so just watch out that. Anyway, now, and I'll produce plus 2 electrons as it shows off the table. And look, the electrons are balanced out, so this is exactly what we can write down. For our net cell reaction, we have Zn plus 2H plus will give us Zn2 plus H2. And that will be a solid, that will be a gas, this will be aqueous because it's in solution, and that will be aqueous because it's in solution. Easy peasy? Yes, it is. Now, let's look at notation. So we said earlier, it is in alphabetical order, it is anode. In its anode electrolyte. Salt bridge, and then we have mirror image cathode electrolyte into the cathode. And if there is a gas, which one of these are, we'll take a look now. So where's what's happening at the anode? Remember, it is oxidation. That will be our Zn. So we have the anode Zn, and the electrolyte is Zn2 plus in solution, and we have salt bridge. And our cathode electrolyte will be our H plus. Remember, no balancing numbers, eh? And then we have the cathode, which is our H2. And because it is a gas, we need a inert electrode, which will be our platinum rod, as we know in our picture there. Okay, so we just put our subscripts in. And we take a look, what else did I want to say? The concentrations for this specific case will be 1 mole per cubic decimeter. And we said it earlier, so we have to have 1 mole per cubic decimeter concentrations and 1 atmosphere pressure for the for the H2 gas that's being pumped in, and also it has to have a constant temperature at 25 degrees Celsius. And remember we said the anode is where oxidation takes place, okay? And that's where electrons are being released. So the Zn side will be negative, and obviously that will then be positive. So we take a look here, electrons are being released, so this will be our negative side, and the electrons will then move in this, sorry, what am I doing? Will move in this, the charge will move in that direction to the left. Okay. So let's do any I should do some E0 electrode potential. Sorry, the cell potential of a galvanic cell. So we use this formula, sort of overthink it, but let's just say we have let's use an example, let's get the formula and then do an example. So E0 of a cell is equal to the cathode minus the anode. And there's like all these other options, but I think that's a nice one because it is constant. So it is for the next section as well. So we have the E0 cell is the standard cell potential in volts. E0 cathode is the standard reduction potential of the half cell in volt, and E0 anode is the standard oxidation potential half cell of an anode in volt. Okay, so it's quite straightforward. These values are on that sheet, that table of standard reduction potentials. So let's take a look at some examples in it's straightforward maths. It's really not easy. Really not, really not difficult. So, right, here's an example out of your guys' textbooks. Calculate the cell potential EMF of the galvanic cell for the following equation. So we have this equation here. First thing we have to do is decide what's being reduced, what's being oxidized. So Cu2 plus goes to Cu0, right? So that is a reduction, it undergoes reduction. And Fe goes to Fe2 plus, which is an increase in oxidative state. So it's oxidation. So that's how we know those that's happening. But now remember, we have to get these values from the table. So we actually have to know what is the anode and cathode, because we're going to be using this equation. You can use another one, but I like this one the most. So remember red cat, so cathode. And oxan, so anode. Easier. So let's use that equation then. We have E0 cell. All right, so you take a nice look at your table. Now, don't worry if it's going to the left or right, if it's being reduced or oxidized. We just take a look, where's a copper Cu2 plus Cu combination, and we just put that value in for the cathode. All right, so I'll quickly take a picture and show you. All right, so let's take a look at where the copper 2 plus is being reduced to copper. It will be this one. Just careful, there is a copper plus somewhere here. Just watch out, we don't want that one, eh? We want the copper 2 plus going to, oh wait, that's also wrong. It's all on. Yeah, there we go, found it. There it is. Just watch out, like 3 copper things here. Just make sure you choose the right one. So there's a copper 2 plus and a copper, and then we have looking for iron, which is going to iron 2 plus. So we're gonna go with that one. Careful, it's also iron 3 plus, we don't want that. So remember now, we don't care, we just know that iron is being oxidized, so it's going, the thing on the top goes to the left always, and the thing below it goes to the right. So we don't care about the direction, we only care about these values. So we're going to plug those values in, no matter if it's being oxidized or reduced, we're just going to plug it in. So let's just say it was going to the right, it doesn't matter, we're just going to, whichever two species are being oxidized or reduced, we're just going to take those values using this specific table where lithium is at the top, while negative value, we start with negative values and we go to positive values at the bottom. Just be careful if there's a graph where the positive, it's like this graph swaps out, this table swaps out. So you want to start with, sort of memorize something that you start with lithium at the top, or with negative values going to positive values as you go down. Just take a little like photographic memory piece here, just in case they swap out the values, or they give you 2 different graphs where they give you the table of standard oxidation potentials, and everything just swaps out. So maybe lithium must be at the top. Okay. Anyway, so we plug those values in. So what's at the cathode? We said it's copper, 2 plus going to copper. So where's that? That value is 0.34. So positive, we're just going to say 0.34. And the anode is, we decided over here using our various little rules that that's where the iron and iron 2 plus goes. But now it's going to the left. We're still going to plug in that negative 0.44. And boom, we get an answer of. We get an answer of positive 0.78 volts. And just for, it's quite important, if your inert cell is a positive, that implies that it's a spontaneous reaction. Okay. Right, so they can give you a whole bunch of different type of questions where they can give you the E cell value, and then they give you an anode value, and they're like, what's the E naught of the cathode, or the thing being reduced, or they'll even ask you like, you know, all these things are interconnected. So they can give you this, and they'll ask you what's that. So you can just plug those values in and find the E anode, E naught anode, and you'll know from oxan which one it is. So that's pretty straightforward. All right. I just want to ask a question over here. Let's just say you put an iron nail in a silver nitrate solution. So you have an iron nail being chucked in a silver nitrate solution. So what happens is you have iron with the oxidative state of 0 and a silver iron in solution. Will this react spontaneously? Will this react spontaneously? So how do we know? We can either use our E naught values, or we can just take a look at our little pattern here. So iron is, let's just take the Fe2 plus, where is it then? Iron nail, that's over here, is going to have to be oxidized for it to react, right? And silver ion is over here, and it will have to be reduced for reaction to take place. So does this make sense? Is the thing above going left, is it being oxidized? Yes. And the thing below it is being reduced? Yes. Therefore, the reaction is spontaneous. So you, in a test, maybe they'll ask you like why, and give say it in terms of reduction oxidation strength, or reducing agent strength, or oxidizing agent strength. So you can say a thing here like iron, Fe, is a stronger reducing agent than Ag. If you take a look at this, the thing above is the stronger reducing agent, and therefore it will cause the Ag plus ions to be reduced. So iron, Fe, over here, is a stronger reducing agent than Ag ions. So therefore it will, or silver itself, and therefore it will reduce silver. So iron, that's what I mean, it's above it. So because this is above this set here, this will get oxidized. It is a reducing agent, a stronger reducing agent because it's above it, and it will reduce the silver ions to silver. Right. All right, so what if we throw some copper nail in a hydrochloric acid solution? Will it be a spontaneous reaction, or will it not be? So let's take a look at our standard reduction potential. First of all, we'll have H plus ions and Cl minus ions in solution. Let's take a look at where the copper is. So find a quick. Oh, there it is. So there's copper. Oh wait, that's the wrong one again. There it is. Copper going to Cu2 plus 2 electrons, so it will have to go in this direction. If we take a look at copper solid, if it's going to react, it's going to form a Cu2 plus. It won't form anything else. All right, so we have hydrogen and chlorine ions in solution. So the hydrogen ions will have to again form H2 gas, and the Cl ions will have to form Cl2. But if we take a look at our copper, we'll always use this, if they talk about copper forming an ion or something, always use this copper, don't use the other ones unless like they're really specific about it. But we have here our hydrogen and our chlorine at the bottom here. Now, chlorine will also go to the left. It'll have to. So it starts as a Cl minus on the right and it will go to the left like this. So this 2 arrows going to the left, it's not going to happen. So we're not going to look at that at all. It won't even qualify. So therefore, but this will work, right? So we have H plus ions in solution forming H2 gas. But remember now, yeah, so this will be what will react, not the chlorine at the bottom, because you can't have two things being reduced. So we take a look at this. Here's our situation taking place here. But remember, the thing at the top must go left, and the thing below it goes to the right. In this case, it doesn't. So it will not spontaneously happen unless there's external help. Right. So in the test, I'll ask you, why is this regarding the reducing agent strength or whatever? So you'll say copper is a weaker reducing agent than H2, and copper is therefore not able to reduce H plus ions to H2 gas, and therefore the reaction will not take place spontaneously. Right, so let's take a look at last year's past paper. I think it's November 2022, the end of year paper, November. So let's take a look at question 8 over here, 8.1 at the top. And let's see if we can figure this out using the knowledge we have just gained. So a piece of zinc is placed in a test tube containing acidified potassium permanganate solution. So we have Zn is put, zinc metal is put in a tube, and it is containing acidified potassium permanganate solution. So that's so nice. They actually give you the ion there. H2MnO4 aqueous. So that's one of the ions. Anyway, so it's saying after some time, it's found that the redox reaction takes place. Use the standard reduction potentials to answer the following questions. That's this story over here. Okay. Write down the name or formula of the reducing agent. That is the thing being oxidized. So we take a look at our standard reduction potentials up there, and we're going to highlight what is taking part. So we have our MnO4, let me just find it, oh, there it is, and we have our zinc, which is all the way up here. All right, so they say that a reaction takes place, so it takes place spontaneously. So anyway, so the zinc is at the top, and this substance is there, zinc is over here, it's going to go in this direction, and that will go in that direction. So therefore, it is a spontaneous reaction. But which one is which is the reducing agent? In other words, what is causing reduction to take place? Remember, to the right is reduction. If you're going left, you're being oxidized. Or you can also think in terms of like what is being oxidized itself. Here's the question. Oh wait, wrong question. There's the question. Reducing agent is the thing being oxidized. Losing oxidation is loss of electrons, reduction is gain. So zinc is the thing being oxidized. All right, so that's quite simple. So we'd say there zinc, easy peasy. 8.1.2, refer to the relative strengths of oxidizing agents to explain why a redox reaction takes place. This is what I was talking about earlier. They'll like to ask this type of thing, but it's quite simple. We take a look at which one is the stronger oxidizing agent. Which one is the stronger oxidizing agent? So taking a look at this table, the weaker reducing agent is at the bottom, and the stronger oxidizing agent is at the bottom, right? So which of these two, between zinc and this whole, whoops, what did I just do? Hold on. All right, fix it. Which of these two is the stronger oxidizing agent? It will be the MnO4, and it will cause the zinc. It's a stronger oxidizing agent than the zinc 2 plus ions, and will oxidize Zn to Zn2 plus. So here's our strongest oxidizing agent from the table, and it will reduce zinc to Zn2 plus. Again, it's lower down. Your MnO4, your permanganate ions, is a stronger oxidizing agent than our zinc 2 plus ions. Therefore, it will cause the zinc to be oxidized. Yeah, so that's how you say it in a test. So if they ask you in terms of reducing agent, you'll just say the opposite thing, right? So you'll say then zinc is a stronger reducing agent than Mn2 plus, therefore it will cause MnO4 to be reduced to Mn2 plus. Okay, so let's take a look at the next one, next question. That wasn't too bad. Standard electrochemical cells are set up here. Take a look at this picture so we can figure out what's happening. All right, so before I even read the questions, I will take a look at my reduction potentials. We have Ni going to Ni2 plus and Mn going to Mn2 plus. So let's find them quickly. All right, so I found them, and just from knowing the pattern or whatever, the thing above will be oxidized and the thing below it will be reduced. So Mn2 plus will be oxidized and Ni2 plus will be reduced. So in our half cell, what's going to happen is our Mn2 plus, our Mn will go to Mn2 plus, meaning we have a loss of mass here, and our Ni2 plus will go to NO, which will be an increase in mass of our nickel electrode. So Mn will go to Mn2 plus and Ni2 plus will go to Ni. I know, it's all on. All right, fix it. So Mn with a 0, so it's being oxidized. This is an oxidation here, and that would mean your anode. Remember, ox-anode, and here it's being, the nickel is being, in solution is being reduced. So this is your red cat, reduction and cathode. Cool, eh? I mean, I think I basically just summarized the whole thing here. So 8.2.1, write down the function of component Y. Y is our salt bridge. So we just write down that it just completes the circuit. I mean, or you can say allows ions movement for ions or path for it, or yeah, to ensure like electron neutrality in the cells. All right, easy peasy, yeah. Then the second question, in which direction will electrons flow in the external circuit? Tells you those two options. So where is our electrons being produced? So they're being produced here, like that, right? So they're being produced by the manganese. So we'll start there and we're going to go in this direction, right? So it'll be manganese to the nickel electrode will be the direction. I mean, this stuff's so easy so far, isn't it? Let's go to 8.2.3. Calculate the initial EMF of this cell. All right, so I forgot what I was doing. So I think we are busy with 8.2.3. So let's hope that is where we ended. So it says you calculate the initial EMF of the cell. So we just write down that E0 equation. So we write down an equation. We have E0 cells equal to E0 cathode. Remember, red cat also E0 reduction, or oxan, or you can also say E0 oxidation. Yeah, so whatever. But I'm just going to go like this because it's nice. I prefer thinking this way. So let's take a look at our values. So we have Mn going to Mn2 plus. Where's that? We highlighted it. So that value is negative 0.08 and negative 1.18. And for the nickel being reduced, we have negative 0.27. So let's plug those values in. So red cat, reduction is the cathode. So this will be a reduction over here, red cat, and over here we have oxidation, increase in oxidative state, and red ox anode. So let's go. I think the first one's a cathode minus anode. So cathode minus anode, we have negative 0.27 minus E0 anode, which is negative 1.18, right? Just double check. Yes. So it doesn't matter. Yeah, you just plug those values in as they stand there, no matter if the thing's being reduced or oxidized. We just plug it in. This negative will tell us what's happening. So if we get a final answer of 0.91 volts, positive value, which means it's a spontaneous reaction, but it kind of does tell you that anyway. And this is, guys, I mean, really, 4 marks for this. I mean, really, 1, 2, 3, 4 marks. I mean, is this not easy? It's like straightforward, easy stuff, this same. All right, 8.2.4. Write down the balanced equation for the net cell reaction taking place. So we sort of did this, like before I even read the questions, I just figure out what's happening before I even answer the questions, because then I feel comfortable, more relaxed and comfortable. So we have Mn going to Mn2 plus, as we decided earlier. And we have, what was the zinc? Oh, nickel, sorry. We have nickel 2 plus going to nickel metal. Let's put our zeros in there. So we have 2 electrons here, and we have 2 electrons here. The electrons can cancel out, and we just get our nets. This is our oxidation half cell, our reduction half cell, and if we just add them together, we get manganese plus nickel ions plus one of them, and then Mn2 plus Ni. Easy peasy. I think it's really, really nice. Really easy that. So we didn't have to deal with the LCMs there. So that'll be, how many marks was that question? 3 marks. Okay, so it'll be for the left-hand side, right-hand side, and for balance, I think. So so far the marks are really easy for this question, isn't it? 8.2.5, what if the concentration of nickel ions is increased in the nickel electrolyte, what's going to happen? Are we going to have an increase in our voltmeter reading, decrease, or will it remain the same? So if we have more of these ions added, and according to the Le Chatelier's principle, whatever, more electrons can be accepted at a higher rate. So what will happen is more electrons will be sent down here, increase in charge being thrown out, so therefore we have an increase in the voltage, so it will increase. Okay. More nickel ions will be converted to nickel metal as well, then increasing the rate of mass gain. So I mean that was 15 marks, and I think that if you just know the logic of it, this is straightforward. Maybe not 8.2.5, need a bit of theory there, but that's straightforward, really straightforward. And over here, that's just like grade 11 work. But then we just need to know a little RAMP, as I showed earlier in the video. Just go through that a few times. So guys, I think you should feel better about galvanic cells. It's really straightforward. One of those more easier sections, a section you should probably study first. Do your past papers and know how to do this reduction table, standard reduction potential table, how to use it. And then it should be straightforward and easy sailing from there, guys. Right, take care. Like and subscribe if you enjoyed this video, and leave a comment for the algorithm if you wish to do so.